Hello, everybody. Hello, everybody. So, welcome to our second part of this lecture. We are still in chapter 4, which is a time response. So, in that part, we need to talk about first order system. As I told you, we will divide systems into first order and second order because all higher order systems can be approximated as a second order. So even if you are working with a second order, third order, or fourth order system, it should be possible to approximate it as a second order system and design your controller because those methods are, in fact, are designed for maybe single order, first order system, and a second order system, and not for higher order systems. So all higher order systems, we assume that you will be able to approximate it as a second order system. So now in this section, we will start with first order system. First order system, the transfer function will be A divided by S plus A. So as you can see here, we have a pool at S equal minus A. So again, I mean, for the definition of pools and zeros, the pool will make G of S equal infinity, right? So at the system pools, G of S should be infinity, and this will happen if it will be something divided by 0. So we need to set S plus A equals 0. So we will get a system pool at S equal minus A. So we will have here a system pool at S minus A. This is my pool in the complex S plane. Complex S plane consists of two axes. One is a real axis and G omega axis, imaginary. And we put S equal minus A. And as you can see here, it is located in the left-hand side of the S plane. This one is the right-hand side. And when you have a pool at the left-hand side, it will generate exponential term, which is k multiplied by exponential minus at. And when it is exponential negative, it means it will decay with time, right? If you try to plot this one, it will be something like this one, right? So it will decay. This is time, and this is the output, y of t, for example. So it will decay over time. When it decays, when it reaches 0, for example, in this case, we can say that, okay, we are in steady state. So this one will be transient response. This one will be steady state response. In steady state response, we will keep one component, and this component will be generated due to the input. So we call it the forced component. So this is the first order system, transfer function of second order system in the figure A, and in figure B, we have this pool plot. We call it pool plot or pool zero plot. Pool plot or pool zero plot. We need to find the output for a unit step. For a unit step, R of t will be 1. When we set R of t equal 1, in this case, R of S will be 1 divided by S. This is Laplace transform. So we need to get C of S, the response. So C of S will be R of S multiplied by G of S. Because G of S equal the output divided by the input. Cross multiply. So C of S multiplied by 1 equal R of S multiplied by G of S. You just substitute R of S 1 divided by S, so it will be A divided by S times S plus A. Use partial fraction expansion because we have this complex fraction. We need to write it as a summation of simpler fractions. So it will be K1 divided by S plus K2 divided by S plus A. Take the limit as S go to 0. So it will be A divided by A, it will be 1. And it takes the limit as S go to minus A. So it will be A divided by minus A, it will be minus 1. So it will be like this one. Find inverse Laplace transform. So inverse Laplace transform, in this case, C of t will be, this one will be 1 minus exponential minus at. So this one will be my response. And the response consists of two parts. It's constant part, which is the forced component, and the exponential part. We call it natural response, or unforced component. This unforced component, it's due to system dynamics, and that part will decay over time, right? So in this case, subtract 1 minus this figure, so the response of your system, it should be something like this one, right? So this one, it's a transient response. and that part is a steady state response. Steady state response. So this is the force component which will stay with us to infinity, but the natural component, it will decay as t go to infinity. Yes. So the time response of the first order system, it will be like this one. So we have input pool as the origin. If we can go back to the transfer function, we have here a system pool at -a, and we should have also input pool at origin. We call it input pool. And it's due to the input. And this one, in fact, it will generate the forced component. So this one is very important because this is input. Without this one, you will not be able to get an output from your system, right? So it's like you just push your car a little bit and that is it. Or switch in the engine and they give it, try to push your car. So it will move a little bit and it will decay, speed will decay because it's due to system dynamics, because it's heavy and there are some maybe fractions and so many forces which are acting on it. So it will stop after short time. But if you want it to keep, on, for example, in this case, you need to provide an input, constant input to your system. This input, it will be generated due to the input pool, and this input pool, it will generate it due to the reference input RFS. So the input pool at the origin, it will generate the forced component or forced response, which is 1. The system pool at s minus a, it will generate the natural response, which is minus exponential minus at. At time equal 1 divided by, if you want to find, if you can substitute at t equal 1 divided by a. So I want to, so here, for example, this is my transfer function. G of s equal, in fact, it was a divided by s plus a, right? So when you substitute for this, for that part, if you can substitute t equal 1 divided by a, this exponential, it will be e exponential minus 1, right? So at t equal 1 divided by a, that part will be minus 1. So the response will be 1 minus exponential minus 1. Exponential minus 1, it's 0.37. So the response here will be 0.63. In fact, 1 divided by a, it's the time constant of your system. And it's the time which the system will take for the step response to rise to 63% of its final value. We know that the final value here is 1. So what is the definition of the time response? It's the time which the system will use or will take to go from 0 to 63% of its final value. Changing the parameters of the first order system will change the speed of its response. But of course, this E, it's the time constant, right? So 1 divided by E, it's the time constant. 1 divided by E, it's the time constant of your system. It's the time constant of your system. It's changing it will change the speed of your system, because this is the time which the system will take to reach 63% of its final value. So if you want to change, if you are able to change this parameter, you will change the speed of your system in the transient response. So this is the response of the first order system. As you can see here, we don't have any overshoots or undershoots. So the time constant, it's the time which the system will take. We are starting from t at equal 0, and at t equal 1 divided by a, when t equal 1 divided by a, we will reach 63% of your final value, which is 1. So this time we call it time constant. This one we call it time constant. So when t equal time constant, if you want to find your time constant from your response, we use this in identification, for example. I don't know my time constant. I don't know what is the value of E. But I know that my response is first order system. So you can do this step test. step input test, right? I will provide the input. I will provide the step input to my system. We will plot the response. We will see when the response will reach 63% of your final value, and this one will be my time constant. So this one t equal 1 divided by a. So if you want to find the a here, if you don't know a, what is a value, so you just need to find this time. Maybe this time will be, for example, 0. Imagine that it's 0.1 second, right? So we can say that, okay, 0.1 second equal 1 divided by t. So in this case, t will be 0.1. Or 1 divided by e. I mean, this is my time constant, in fact. So time constant will be, maybe time constant will be 0.1. And this time constant, it will be, I mean, this a coefficient, it will be 1 divided by e equal t. So in this case, you can just say that this one will be 0.1. So in this case, cross multiply. So a will be 1 divided by 0.1, which will be 10, right? So I can find the a from this. We call it system identification. So a equal 1 divided by time constant. This is the idea here. A equal 1 divided by time constant. So if you can find the time constant from the graph, you can find a, because a will be 1 divided by this time constant. If the time constant equal 0.1 second, so a will be 1 divided by 0.1, which means a equal 10. So, because how can we find that my response is, my system is first or second order? Just, you have your system. I don't know my transfer function. It's unknown for myself. So we will provide here step input, and we will plot the response of your system. If the response looks like this one, without overshoot or undershoot, you can say that, okay, my system is first order system. Correct? You will just try to see when this is the final value, which is 1. And I will see when the system will reach 63% of its final value to be something here. So I can say, okay, this one is my time constant. And I need to write the transfer function. So the transfer function will be maybe 1 or a divided by s plus a, correct? And the a will be 1 divided by t, correct? Maybe here this one will be k, correct? I don't know. So now we found a. You need to find the k. It's also, you should possible to find the k. If you can reach 1, it means the k equal 1. If you can reach 0.5, it means k equal 0.5, right? So in this case, you can find the parameters from my response. So the most important here is the time constant. And the time constant is the time which the system needs to reach 63% of its final value. So just to block the response of your system. But the most important here is that you are able to reach this one, right? So this one will be my time constant. Transient, we have also something called settling time, and we know the definition of the settling time. And settling time, in fact, it should be around 4 time constants. 4 t. So it's 4 time constants. And it is a time which required to reach 95% of the final value, right? We have also something called rise time. And as you can see here, the rise time is the time required for the system to go from 10% to 90% of the final value. We call it the rise time. So if you need to calculate the rise time, so the rise time is the time which is required for the response to increase from 10%, this one it's 10%, to 90% of the final value. This is the rise time. So you have time constant, you have rise time, you have settling time. Settling time, it's more or less 4 time constant. Settling time is around 4 time constants. So those are the parameters which can be used to characterize your time response of the first order system. So the performance, the specification of the transient response. So I mean the response in time domain, it will be like 1 minus exponential minus at. So the definition of the time constant is the time it takes for the step response to rise to 63% of its final value. Right, this time constant, it will be 1 divided by e. A, it's your pole location, right? So if in pole 0 location, in pole 0 plot, so you will get something at minus A, 1 divided by this part, 1 divided by A, absolute value, you cannot use time is positive all time. So 1 divided by A is your time constant, right? So which means when you are closer to this G omega axis, T will be smaller, or A will be smaller. When A is smaller, T will be what? T will be, when A is small, T will be large, right? So when you are closer to the G omega axis, your response will be slower. When you are far away from the G omega axis, what will happen here? So A will be large. So A divided by something large, it will be very small. So in this case, the time constant will be very, very small, which means your system will be faster, right? So just remember, we can have it as a question, for example, right? Which one will be faster? Which one will be slower? So when your pole is far away from the G omega axis, if it is first order system, for example, what will happen? What will be the response in this case? What will be the response in this case? Correct? So when it's a closer, I can just give you a response like this one. Okay, you have a system pole here, correct? And you have a system pole here. So what will be the response? Choose the response, right? So the response here, it will be something like this one, or something like this one. Here the time constant, it's larger. The time constant here is smaller, right? Just remember that this one is A. Time constant will be 1 divided by A, right? When A is large, C will be smaller. So in fact, this one is the response of this one. When you are far away from the G axis, your response will be much faster. Because this exponential something negative large value, it will decay faster. When it decays faster, it means your system is much faster, right? So this is the response of that part, and this is the response of that part. Just remember it. So if you want to find the solution of the value of A or T, for example, you can solve this equation for C equal 0.63 because it's 63% of the final value. So if we can put this one 0.63 equal 1 minus E minus minus 80, right? Minus A multiplied by T capital, which is the time constant. If you can solve this equation, you will be able to find the time constant. So time constant will be 1 divided by A. When you solve this equation, time constant will be 1 divided by A. Just remember, time constant is 1 divided by rise time. It's the time required for the response to go from 10% to 90% of its final value. And this rise time, it will be around 2.2 your time constant, or 2.2 divided by A, because time constant is 1 divided by A. And it's the same way. So if you want to solve it here, you need to get two equations and solve it. So you need to substitute for C equal 0.1 and C equal 0.9 and solve this equation. You will find that rise time will be 2.2 time constant, or 1 divided by A. Settling time, it's the time for the response to reach and stay within 2% of its final value. Yeah, it's 98%, right? 2% of its final value. And this settling time, it will be 4 time constant, 4 divided by A, or 4 multiplied by the time constant. So it's very important to remember that for the first order system, the time constant, it will be 1 divided by A. The rise time, it will be 2.2 time constant, and the settling time, it will be 4 time constant. If you want to get this exact solution, you need to solve this equation for C equal 98% of the final value, which is 0.98. Changing the parameters of the first order system will change the speed of its response. So if you can change A, you will be able to change the response of your system. And this is possible, right? If we can close the loop, Maybe your system is very slow. I'm not happy with this response, and I need to speed up. How can we do this? By using a closed loop system and designing a controller which will reallocate your pool, because my pool here it's located closer to the G omega axis, and in this case my response is very slow. So I need to use pool reallocation or pool zero. We need to design a controller to reallocate the pool so I can speed the response of my system. I'm not happy with this response because the pool is located closer to the G omega axis. I need to have a response like this one. So in this case, I can use this pool zero cancellation. For example, I need to cancel as a location of this pool, and I need to put a different pool in a different location, which will give me the desired response, right? It's called pool zero placement. In fact, it's called pool zero placement. So we need to replace or place my pools or reallocate my pools to different locations, which will provide the desired response. Solving for rise time, I mean, we will go to the equation and try to solve it for the rise time. So this is the response, C of t equal 1 minus exponential minus AT. For the rise time, we need to get two equations. So the first equation will be the time at 10%. And in this case, we will substitute the output equal 0.1 as the time which at 90% of the 0.9 of the final value. In this case, the output will be 0.09. So this exponential part, it will be 1 minus 0.1, so it will be 0.9. Take length of both sides, so minus a multiplied by t 0.1. It will be length of that part, so it will be that part. So in this case, this time will be 0.105 divided by a, right? Which is like 10% of that time. 1 divided by 8 is the time constant. You will solve the second equation, take length of both sides. So minus a times t 0.9, it will be length 0.1. So it will be minus 2.302. So in this case, T009, it will be that value divided by minus a. So it will be 2.3 time constant. We subtract, because the rise time, it will be this time minus this time. So subtract equation 2 from equation 1. So the rise time, it will be time at 90% minus time at 10% of the output. So it will be this one minus that part. So it will be 2.19 divided by a, which is approximately 2.2 time constant. Time constant equal 1 divided by a, right? So it will be approximately 2.2 time constant. Len x, of course, represent natural algorithm of x. So the first order transfer function by testing, this is very important. How can we get the first order? How can we get the transfer function of the first order system by testing? Because sometimes it's not possible to obtain the system transfer function. You have a system and you don't have the transfer function of it. You don't have a differential equation. So you can't find the transfer function analytically. So in this case, we need to do a test in order to plot the response and try to find the parameters of your transfer function of your first order system. So perhaps the system is closed and the component parts are not easily identifiable. Maybe you have a system in the lab from 1940 and there is no manual, for example, there is no equations, there is no information about the system. And if you try to open the system and analyze it and try to find its component, maybe you will damage your system, or it's difficult to do this. So in this case, we can try to find the transfer function by testing. Transfer function is a representation of the system from input to output. So we will use a step response, which can lead to a representation of the inner construction, even if the inner construction of your system is not known. So if I can provide my system with an input, I just need oscilloscope and I need a step input. So I have a system, maybe the system is a motor or something which we don't know. So I will just provide a step input to my system. And in the oscilloscope, we will try to see the response. How the response look like? If the response look like this one, now it's first order system. If the response looks like this one, maybe it's a second order or third order system, right? Or approximated as a second order. So just provide a step input to your system and look into the response. If the response looks like this one, now it's first order system, and we can say, okay, the transfer function will be k divided by s plus a. If this one, now it's a second order system, right? So, and we will study the transfer function of the second order system. So with the step input, we can measure the time constant and the steady state value from which the transfer function can be calculated. I need to find the A and I need to find the K. From this response, we will see when the output will reach 63% of the final value, and we will call it, this one will be my time constant. And once you find this value, you can find the A, because A will be 1 divided by T. Correct? And after that, we will get K. Because K will be this value divided by the input, right? So this is the response. Consider that you have a system. This is the first order transfer function, K divided by S plus 1. So C of S will be K divided for step input. It will be K divided by S plus this one. Use partial fraction expansion. So that part will be K divided by A. That part will be minus K divided by A. So at the end, response will be like this one, K divided by A minus K. This is constant value, which is the output at steady state. This is the force component, and this is a natural component. We need to find the time constant. So in fact, we need to just measure it. Right, so this one will be my time constant because this is T. Correct? So time constant, it's T equal 1 divided by A, is the time required to reach 63% of its final value. It means 63% of the final value, it will be 0.4, because the final value here, it's not 1, in fact. Sorry, I mean the final value here, it's not 1, it's this value, right? So it's the time which is required to reach 63% of the final value. So the final value here, it's 0.72. So 63% of it, it will be 0.45. So 0.45, it will be here. So this one, in fact, it will be my time constant. This one will be my time constant. When you look into the time axis, time constant, it will be around maybe 0.13 seconds. It will be that part, 0.13 seconds from the graph. So 1 divided by A will be equal T, which is a time constant. Cross multiply, so A will be 7.7. So now I can say, okay, my transfer function will be something divided by S plus 7.7. Now we can find the A. Now we need to get K. What is K? It's a steady K divided by A. It's a steady state response. So the final value here, in fact, it's a K divided by A, which is 0.72. Cross multiply, so K will be 0.72 multiplied by A. What is A? We got A already, which is this 7.7. So it will be 0.72 multiplied by 7.7 equal 5.54. So in this case, your transfer function will be 5.54 divided by S plus 77. So it's by testing. So now we can get the transfer function of the first order system by testing. So even if you don't have, but we need to do a step test. So I need to have my system, and for my system, I will provide an input R of T equal 1. Plot the response, so it will be something like this one. When you solve it in the time domain, you just know that the output at the steady state will be K divided by A. This is very important because I need to find the K. We assume that the transfer function will be K divided by S plus A. I need to find the A. I need to find the time constant. A will be 1 divided by T. Now we got A. The output at the steady state, it will be K divided by A, as you can see here, K divided by A. You know A. Once you know A, you know this value. So cross multiply, you can find the value of K. So now we can find my transfer function by testing or by inspection. So the transfer function will be that part. So even if you don't have the differential equation of your first order system, you can get it by inspection or by testing. We have here an exercise, a system which has a transfer function equal that part, find the time constant, split in the time and rise time. Easy, 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 right? Quickly, this one, it's S plus A, correct? So now we have a pool at minus 50, correct? So A equal 50. So time constant will be 1 divided by A. It will be 1 divided by 50. So it will be 2 divided by 100. So it will be 0.02 seconds. This is my time constant. What about settling maybe rise time? So we know that rise time approximately 2.2 time constant. So it will be 2 times 2 multiplied by 2 times 2 multiplied by 0.02, right? So it will be okay. Rise time, yes, that part. So it will be this value. Just multiply this one by this one. It will be 0.044 seconds. Settling time is approximately equal 4 time constant. So it will be 4 multiplied by 0.02. So it will be 0.08 seconds. So very quickly. So once you have the transfer function, you can, in fact, without plotting. Why you are doing this, in fact, because maybe long time, many years ago, it was difficult to plot the response of your system in the time domain because we don't have computational resources. So once you know A, you can find time constant. From time constant, you will calculate rise time. From time constant, you can calculate settling time. So even you don't need to plot the response. You can just plot it by paper, for example, and you can say, okay, this is my time constant. This is my rise time. This is my settling time, right? Without plotting it. So now you can see, you can have an overview of the response of your system without simulating it. Now we will go to second order system. So changing the parameters of the first order system, it changes the speed of its response. Yes, of course. If you change A, the speed of your response will change. And as an example, assuming that your transfer function is like this one, it's K divided by S plus A, right? So if you change K, it will, because the response here in time domain, it will be K divided by A minus K divided by A exponential minus AT, right? So T, in fact, first of all, T equal 1 divided by A. If you can change A, you will change time constant. And if you change time constant, you will change rise time, which is 2.2 time constant. You will change settling time, which is 4 times time constant. So if you change it A, you will be able to change the speed of your response. And of course, changing a K, it will change the steady state error, because the forced component will be K divided by A. If K equal 1, if K equal 1, A, in this case, the part will be 1, which means the steady state error equal 0. So also, this also coefficient, it will change steady state response. So changing the parameters of the first order system will change the speed of its response. Changing the parameters of the second order system also will change the form of the response. I mean, when it is a second order system, changing those parameters, it will change the form of the response, not the speed of the response. Because in second order system, it's more complex than a second order system, right? We have overshoot, undershoot, many things. So when you are changing those parameters, it will change how it will look like. It could be underdamped, which is this one. It could be overdamped. When it's overdamped, it will be like a response of a first order system, or it could be critically damped. Critically damped, it will be like this one. So, or undamped, in fact, undamped, it will be just, it will unbound it. So the unit step response can be found using, we know it now, if you have the transfer function, right? G of S, your input is R of S, and your output is C of S. So C of S will be G of S multiplied by R of S to C of S equal G of S multiplied by R of S, where R of S will be 1 divided by S for unit step. You need to do this so we can get C of S, and you will follow it by partial fraction expansion. Partial fraction expansion, it will convert this complex fractions into a summation of simpler fractions, right? And after that, we will apply inverse Laplace transform to get C of T. Can the poles tell us the form of the response without tedious calculations of the inverse Laplace transform? Of course, when we look into I mean, here in this example, for example, if you know the location of your pool, you will be able to see how the response will look like of the first order system, the speed. By looking into A, we will be able to see, we can see that, okay, if the response will be fast or slow. So you have, for example, a response which is 50 divided by S plus 50, and another one which is 10 divided by S plus 10. Which one is faster? By looking into the location of the system pool. Here, I mean, it's easy. Time constant here will be 1 divided by 50, which will be 0.02 seconds. It's very quick. But here, for example, time constant will be 1 divided by 10, which is 0.1 second. Which one is faster? When time is shorter, it means it's faster, right? So this one is faster. So when you look into the location of your pool, if it is far away from the G omega axis or closer to the G omega axis, when it is far away from the G omega axis, your response will be much faster. So this one will be faster than this one. So by looking into the pools, it will tell you the form of the response without tedious calculations of the inverse Laplace transform and without the need to simulate your response. So we can look into some general. This is a general transfer function of the second order system. It will be B divided by S squared plus AS plus P. So this is a transfer function of the second order system. This is the general form. SP divided by S squared plus AS plus P. This is the overdamped system. When you look into this response, it's look like when it's overdamped, as you can see here, it looks like, in fact, first order system, right? Except that part, because this red one, in fact, it's a response of the first order system. But because of that section here, you can discover that this one, it's a response of an overdamped second order system, right? So what will happen here? We need to find the characteristic polynomial or characteristic equation of the system. So it will be S squared plus 9S plus 9 equals 0. You can use the law because it's difficult to factorize it. So we can use this law by law. So it's you can find roots. So the roots will be minus 7.8 and minus 1.14. Both are real. Both are located on the real axis. When both are located on the real axis, your response will be overdamped. So when you look into, when you look into this one, it's like multiplication of two first order systems, correct? It's like multiplication of two first order systems. When your poles, you should have two system poles. When your two system poles are located on the real axis, it means your response will be overdamped. So you will get this response without calculation. For the other example here, we have here S squared plus 2S plus 9. So in fact, we have here two complex conjugate pools. It's too complex and the conjugate. It's imaginary, right? It has real part and imaginary part. So in fact, it's S1 and S2. So S1 and the 2, it will be minus 1 plus minus J square root of 8. So it's like this one. So it consists of real part and imaginary part. So when you look into it like this one, it will tell you that your response will be underdamped. Underdamped, this is the best cases, in fact, because we wish that all systems will be underdamped. So when you look into the location of your system pools, you will be able to see that, okay, my response will be like this one. So also for the exam questions, we can have an example like this one. I can give you a figure like this one and ask you to select the response. Is it this one or this one? I can give you a response or pool zero plot like this one and just ask you how the response will look like. Is it this one or is that one? You need to select. This is the response of the underdamped and undamped system. It would be like this one. When it is undamped, it will be like this one, undamped. So it's we have here S squared plus 9 equals 0. So S square equal minus 9. So S1 and 2, my roots will be plus minus J3, correct? So both poles are imaginary, located in the G omega axis. So when it is like this one, your system will be undamped, correct? Undamped. Critically damped, it will be repeated, right? So this one, in fact, when we factorize it, so it will be S9, it's a 3 times 3, so it will be S plus 3 squared. So it's real and repeated equal 0, right? So in fact, S1 and 2 equal minus 3. So both poles are real and repeated. When it is real and repeated, you will get this response, which is critically damped, right? It will be critically damped. So when it is overdamped, just try to differentiate between overdamped and critically damped, right? Overdamped, they are real and distinct. So I have two real poles, two different real poles. But if you have two repeated real poles, it will be critically damped. So this is the response of the second order system. So even without calculations, when you look into your transfer function and define values of your poles or roots of the characteristic equation or characteristic polynomial of your second order system, you will be able to imagine how the response will look like. So this is a general second order standard second order transfer function with u as the input variable and y as the output. So it will be y of s. This is my system. So if your system is u of s, the output is y of s. So your transfer function, it will be k multiplied by omega node square divided by s square plus 2. It's zeta omega node omega 0 s plus omega 0 squared. This is the general form of transfer function of your second order system. So in this case, y of s will be this transfer function multiplied by u of s. So y of s will be that part multiplied by that part. K here, it's the gain. Zeta, it's relative damping factor. We need to find this zeta. I mean, when you look into the transfer function, when you have a transfer function, you need to compare it with a general form and try to find the k by comparison. You can try to find the value of k, which is the gain. Zeta, which is a relative damping factor. And omega node, which is undamped resonance frequency. Omega node, it's a radian per second. It is a undamped resonance frequency. So you need to find those three parameters from the. You need to find the k. You need to find this zeta. You need to find omega node. And the transfer function, as we agreed, it will be k omega node square, or just you can divide by omega node square. So it will be k divided by s divided by omega node square plus 2 zeta. In fact, this form is not good. We just focus on that one, right? So the transfer function will be k omega node square divided by s square plus 2 zeta omega node s plus omega node square. K, it's the gain. Zeta, it's a damping factor or relative damping factor. And omega node, it's the resonance frequency, undamped resonance frequency. So this is the transfer function of the second order system. The shape of the time response y of t, which is calculated as the inverse Laplace transform of y of s, because we need to get y of t from this one, depends on the poles. It depends on the location of your poles. Poles are the roots of the characteristic equation. Your poles are the roots of this characteristic equation, which is s squared plus 2 zeta omega node s plus omega node s squared equals 0. You need to maybe factorize this one or use the law, for example, and try to find a location of your poles P1 and P2. So P1 and P2, it will be using the law, right? It will be it's like a s squared plus ps plus d equals 0, if you can remember. APC, sorry, this one C. So it will be minus a plus minus square root b squared minus 4ac divided by 2a. You need to use this law. If you will do this, you will get those location. It will be minus zeta. So I can do it, yes. If I need to apply this one here, so it will be P1 and P2 equal minus a. Minus a, it will be minus, it's the coefficient of s squared, it will be minus 1, right? So the minus b, minus a, I need to check law. So it's ax squared plus bx plus c. So the formula will be minus p. Yeah, this one minus p plus minus square root b squared minus 4ac. Yeah, this one minus p. Sorry, I did a mistake. This one minus p. So in fact, the law, if you have an equation which ax, for example, ax squared plus px plus c equals 0. So if you want to get the roots, which is x1 and x2, for example, so it will be minus p plus minus square root b squared minus 4ac divided by 2a. It will be like this one. If we need to apply this one to this equation, so it will be minus p, this coefficient of s, it will be minus 2 eta omega naught plus minus square root b squared. It will be also that part squared, so it will be 4 eta square omega naught square minus 4ac. ac, it will be minus, I need to a better space, so I will do it one more time here. B1 and 2, so it will be minus p, it will be minus 2 eta omega naught plus minus square root b square, so it will be that part square, so it will be 4 eta square omega naught square minus 4ac minus 4 omega naught square divided by 2a, which is 2, right? So just divide by 2, so it will be minus eta omega naught plus minus. We will take 4 from inside divided by, it will be 2 outside, so it will cancel each other. So, and omega naught square, we will take it out. So it will be square root zeta square minus 1 multiplied by omega naught. So it will be that part, right? Yeah, so this one, it's just by, you need to use this equation to solve it, to get P1 and P2. Value of zeta, it determines whether the poles are real or complex conjugate. If it is real, for example, so it's located on the real axis, or complex conjugate, which is like this one. When it is real, in this case, we can say that, so the value of eta, because this eta is very important, right? If eta is greater than 1, so this square root will be positive. When it is positive, it means it will be real. So when zeta is greater than or equal 1, the poles will be real, right? I mean, because that one, square root of zeta square minus 1. If zeta square minus 1 is greater than or equal 0, it means zeta square is greater than or equal 1. And in this case, this square root, it will be positive. That part will be positive. So the square root, it will be just real part, not imaginary part. When it is the real part, what will happen? Your response will be, your poles will be located on the real axis. So it will be like this one, repeated, it's real and repeated, which means that your system response will be critically damped, or it will be over damped, right? Because it's real. But if it's not real, your response will be complex conjugate. So your response will be underdamped or undamped. It's according to the real part. So if you have this complex part, and if you don't have a real part, it means your system response will be undamped. It will be like this one. But if you have a real part, it will be underdamped, right? So this zeta, it's very, very important. So when zeta is greater than or equal 1, the poles are real. So in this case, you have two options. Your response will be either it will be critically damped or overdamped. So you will be critically damped or overdamped. So in this case, you have two options. So overdamped or critically damped. Right? You have those two options. But when zeta is greater than or equal 0 and less than 1, the poles are complex conjugate. When it is complex conjugate, you have also two options. So maybe you will be underdamped or undamped. So in this case, you will be underdamped or critically damped. Right? So it will be like this one. So zeta, I mean, this zeta is very, very important. So at the end, your poles, B1 and B2, it will consist of real parts and imaginary parts. In this case, when zeta is greater than or equal 0 and less than or equal 1, in this case, you will get this complex part here, G, right? So in this case, your poles will consist of a real part and imaginary parts. If you have real part and imaginary parts, you will be underdamped. If you don't have a real part, what will happen? Maybe zeta equals 0, right? When zeta equals 0, what will happen? That part will be 0. So in this case, you don't have a real part. When you don't have a real part, you will be critically damped, right? Your response will be, sorry, you will be undamped. Yeah, so you will be undamped. So will be undamped. So your response will be like this one. Here, in fact, zeta equal 0, right? Because you don't have a real part. Here it's complex conjugate and you have a real part. So in this case, it will be underdamped. Maybe here eta will be less than 1, but not 0. So maybe it could be like 0.5, for example. So the damping ratio, it's 0.5, which means you will damp anyway, but after some time. Of course, if it's closer to 1, right? So if it's 0.95, for example, your system will damp it much faster. So this is a damping ratio, damping factor. We call it relative damping factor. So this relative damping factor is very, very important. This undamped resonance frequency, this is the frequency of that part, right? The undamped natural frequency, undamped natural frequency. So, I mean, the conclusion here is that your second order system will be defined by two important factors. Those factors are zeta and omega, omega node, and AK, of course, right? But the most important here is zeta, right? And the natural frequency, undamped natural frequency, which is omega node. Those are very, very important. So when we have been working with first order system, we had only a system pool, and from this system pool, we can find the time constant, and from this time constant, we can try to look into, we can divide systems into maybe fast and slow. But when it is second order system, the parameters here, it will control the shape of the response, right? As you can see here, the shape of your response. Yeah, so when you change zeta and omega node, you will just zeta, just imagine about zeta. So here, it's when zeta is less than 1, for example, you will get a response like this one. It's undamped, underdamped. And when zeta equals 0, it's undamped. It will just oscillate, right? Your system will oscillate all time because there is no damping ratio here. Relative damping ratio here equals 0. But when it's greater than 1, right? So in this case, no, it's a different case now. It could be, in this case, in fact, the two poles will be real. We will not have any imaginary parts. but if it's repeated, it will be critically damped. And if they are distinct, it will be over damped. So zeta is very important, and from this zeta, which we can find quickly from the transfer function, it will be possible to find the form of the response, the shape of your response. Yes. So now we will go into the general second order system. So this is pole placement for second order system when poles are complex conjugate. I mean, those poles are, when those poles are complex conjugate, so we have one pole here and one pole here. So the real part here, because we will go back to the equation, so P1 and the 2 will be the real part minus eta omega node or omega 0 plus minus j square root 1 minus eta square omega node. So this is the real part. This is the imaginary part. So minus zeta omega node, this is the real part. It's complex conjugate poles. So this is the real part. And this is the imaginary part. Right? So this is the real part. This is the imaginary part. There is omega node. If you want to find omega node, so omega node, it will be the distance from the origin to the pole. So it will be this one, omega node. Right? Because, I mean, this is, we know this one. I mean, you use this one. In fact, it will be square root. It will be square root of that part square plus that part square. So if we need to find how this one, I mean, what is the length of that part? So this part will be square root of that part square, which is eta square omega node square plus this one g square, it's minus 1 multiplied by 1 minus zeta square. So it will be 1 minus zeta square multiplied by omega node square, correct? So it will be square root of that part will cancel that part. So it will be square root of 1, in fact. It will be square root of omega node square. So it will be omega node square, omega 0 square, right? Which is a natural frequency. So take square root of that one. So it will be omega node. So the length of that part, it will be omega 0, right? Which is a natural resonant, which is undamped natural frequency. So if you want to find natural frequency, you need to find the length of the distance between the origin and the pole. This one will be omega node. This one also will be omega node. So if you want to find the natural frequency. Yes. So this is the general second order system. If you have, we will look into the value of zeta. If zeta equal, why we start with this one? If zeta equals 0, what will happen? We don't have any damping ratio. So the damping ratio equals 0. So your system will oscillate. It will be undamped. The response will be like this one. It will be undamped. When it is less than 0, what will happen? When it is less than 0, in this case, your system will be unstable. It will be unbounded because the damping ratio is negative. So it will explode, in fact, right? So it will just, I mean, this response will keep increasing until it goes to infinity or until the system is breakdown. So this one, when zeta is negative, it means you don't have any damping ratio. It's like you try to brake your car, but instead of braking and lowering the speed, it goes up, it accelerates. So the damping ratio is negative. When this value is greater than 0 and less than 1, it's underdamped. Well, this is so in this case, my poles will be complex conjugate. It will be like this one, complex conjugate poles. We will have complex. So when zeta equals 0, it will be imaginary poles. When it is complex, when it is greater than 0 and less than 1, it will be complex conjugate, and your response will be underdamped. So this is a general form where we will continue working with that one. When zeta equal 1, in this case, when zeta equal 1, it will be real and multiple, or real and repeated. Your poles will be real and repeated, and in this case, it will be critically damped. It will be critically damped. when zeta is greater than 1, it will be over-damped, real and distinct, real and distinct. You will have two pools which are real and distinct, and in this case, your system will be over-damped. Over-damped, it's similar to, in fact, first-order system response, right? So when it is real and distinct, or when it is real and multiple, we can say that here it's zeta greater than or equal 1. When it is equal 1, it will be critically damped. When it is greater 1, it will be over-damped. When it's less than 1 and greater than 0, it will be complex conjugate and the system will be under-damped. When it is equal 0, my poles will be imaginary. And in this case, my system will be undamped. Undamped means it will oscillate. When it's negative, when zeta is less than 0, it means we have negative damping ratio. So in this case, it will be real and both have, positive and negative real parts. We will have this positive and negative real parts, and in this case, my system will be unstable. Yes. Now we will start with working with case by case. We will try to investigate case by case. So we will start with overdamped system when it is overdamped, right? So when it is overdamped, we agreed that the eta or zeta, it will be greater than, it's greater than 0 and less than 1, right? Yes, so it's greater than 0 and less than 1. So zeta will be greater than 0 and less than 1 because it's overdamped, right? Sorry, greater than 1. Yes, when it's greater than 1, so my system will be overdamped. We have this example, 9 divided by s squared plus 9s plus 9 equals 0. If you want to find, if you want to just compare this one with the general form, so the general form will be is a characteristic polynomial s squared plus 9s plus 9. So this one will be s squared plus 2 zeta omega 0s plus omega 0 squared equals 0. So if you want to find omega 0, so omega 0, just by comparison, omega 0 squared will be 9, so omega 0 will be 9, will be 3 rate per second. This one, it's rate per second. 2 zeta omega node equal 9 equals the coefficient of s. So in this case, zeta will be 9 divided by 2 times omega node, which is 3. So it will be 9 divided by 6. 9 divided by 6, it's 1. Okay, it will be 3 divided by 2, so it will be 1.5, right? So here zeta is greater than 1. For this system, zeta equal 1.5. So it's greater than 1. So the system here is overdamped, right? We need to find the my poles. So we will use the law. So it will be P1 and 2. So it will be minus P plus minus square root B squared minus 4AC divided by 2A. So it will be minus P, it will be minus 9 plus minus square root B squared, which is 81 minus 4AC, 4 times 9, it's 36, right? Divided by 2A, which is 2. So it will be minus 9 plus minus square root 81 minus 36. I need to calculate that. So my calculator, 81 minus 36, it's 45 divided by 2. So it will be minus 9 divided by 2 is minus 4.5 plus minus square root. My calculator, I need to use maybe another calculator, square root, square It's 6.7 divided by 2. So it will be 3.35, right? It will be like this one. So minus 4.5 minus 4.5 plus 3.35, so it will be minus 1.15. Yes, so it will be this one. So the first one will be this one. So P1, for example, it will be minus 4.5 plus 3.35, so it will be minus 1.15. So this is the first one. B2, it will be minus 4.5 minus 3.35, so it will be minus 7.85. Yeah, so this one will be the second one. So as you can see here, both B1 and B2 are real and distinct. Real and distinct, right? So in this case, my response is overdamped. And overdamped, how can we find that it's overdamped? Try to find zeta. And we find zeta, and zeta is 1.5. 1.5, it's greater than 1, right? So my system is overdamped. If you want to get the time response, so C of S will be C of S equal this one multiplied by R of S. So it will be 9 divided by S multiplied by that part. We cannot factorize, but we found the roots of this characteristic polynomial. So it will be S plus 115. And this one will be S plus 85, right? We found it here. Use partial fraction expansion. So it will be K1 divided by S plus K2 divided by the second one plus K3 divided by the third pool. So apply inverse Laplace transform. So it will be K1 plus K2 exponential minus 7.85t plus K3 exponential minus 1.15. But by inspection, we don't care about values of K1 and K2. So that part would be the natural component or unforced component. And you can see the exponential is negative. So this one will decay. This one is the forced component, right? Forced component. So now we can. So finally, when you solve for K1, K2, K3, you will get those values here. If you want to solve, try to solve it and try to get those numbers. And the response will be like this one. So please try to solve this problem. Try to find the value of K1, K2, and K3, and try to put it in your for loop in Python, and try to get the same response. Plot it for t from 0 to 5, and try to check if you can get the same response. So this one, it's overdamped response. And in the, just to summarize, in the overdamped response, we have two real pools on the real axis, two real pools on the real axis. This one real axis, this one imaginary axis. The input pool at the origin generates the forced response. We will get one here from the input. Remember, we call it input pool. This input pool, it will generate the forced component, which is that part, right? Which is one, right? This is the forced component. But this one, it's a system pools, and those system pools, it will generate the natural component or natural response, whose exponential frequency is equal to the pool location. Yes. Right? So, in fact, yeah. Okay, so this is overdamped. Overdamped response. The step response has no overshoot. As you can see, don't have any overshoot. This one, it's overdamped. So the step response has no overshoot. The B1 and the B2 are real and distinct. Can get it like this one. The transfer function can therefore be written on the form. It could be written in this form. S minus P1 times S minus P2, because we will get B1 and the B2. So we will have here B1, we will have here B2, correct? So, and you can just replace B1 by, you can say that, okay, B1, it's 1 divided by T1. Just replace B1 by T1, B2 by 1 divided by T2. So in this case, we can say that we can split the second order system, in this case, into two first order subsystems having time constants equal T1 and T2, respectively. The largest of these time constant can be denoted as the dominating time constant. So you have P1 and P2, right? We have here, we will call this one it's P1, this one it's P2. This one will generate a time constant equal 1 by divided by T1 or T1. Sorry, I can call T1 equal 1 divided by B1. This one will generate a time constant called the T2 equal 1 divided by B2. B2 here it's the largest. So in fact here T1 will be largest than T2. Correct? It's 1 divided by small value, it will generate bigger value. So T1 will be greater than T2, right? Which will be faster, right? So we can say that H1 will generate a first order system with time constant T1 and T2 respectively. The largest of these two time constants can be denoted as the dominating time constant, right? One will be dominating the. So anyway, we can say that this overdamped response will be more or less a response of a first, or it looks like a response of the first order system, but you will discover it if you do a tested response. When you see this bulge here, it will let you know that this response is a second order and it's not a first order. If it is first order, it will be clearly like this one. But when it is a second order overdamped, it will be like this one. So you will look into this bulge here, it will let you know that this response is a second order system. But also, if you want to represent it as a first order, it's okay. We don't care, correct? So if you want to represent this response as a first order, you can approximate it as a first order system. It will be fine, no problem at all. So if I need to represent this one as a first order, it will be 1 divided by S plus A, and A, it will be 1 divided by T. So I just need to find this T value, right? Correct? So I will find S 1 divided by S plus 1 divided by T. So this one will be the dominating first order response. So overdamped response, it can be decomposed into a multiplication of two first order systems, right? But one of those will be dominating. And if you want to simplify life, just assume that it's a first order system. No one cares, right? It's okay. We don't have a problem. We don't have a problem with that part. But just to differentiate, if you have this bulge here, it's indication that it's a second order system, not first order, right? So it could be also an exam in the question. I can give you a graph like this one and a graph like this one, and ask you to write maybe which one is first, which one is second, or can you approximate this one as a first order system, right? So anyway, this overdamped system, it's a system which has two poles, two real poles, and distinct. Two poles are real and distinct. If those two poles are real and repeated, what will be the response? It will be critically damped, right? It will be like this one. It will be critically damped. So it's overdamped here. So are here overdamped or critically damped, right? When zeta is greater than 1, because in our case it's 1.5. So when it's greater than 1, it will be overdamped. When it's equal 1, it will be real and distinct, multiple, repeated. So in this case, it will be critically damped, which looks like also first order system, right? So now we finished over damped. We will go to under damped. Under damped, this is a general case. So this is it will be complex conjugate poles. We will have two complex conjugate poles, which means it has real part and imaginary part. The response will be like this one. So this is a characteristic polynomial. We need to. So it will be s squared plus 2s plus 9 equals 0. If we will use the law, so p1 and p2, it will be minus p minus 2 plus minus square root b squared. It will be 4 minus 4 AC, so it will be 2 times 4 AC, it will be 4 times 9, 36, divided by 2, it will be like this one. So it will be minus 1, plus minus. It will be, we can take 4 outside this one. So it will be square root minus, it will be square root minus 8. Correct? So it will be minus 1 plus minus j square root 8. What is the square root of 8? Yes, it will be just the square root of 8. Yes, it will be like this one. So as you can see, if we need to block it, it will be in this real part, imaginary part. So we have the real part -1. So we will have here -1. We have imaginary part. It will be plus j square root 8. This one will be minus j square root 8. So it will be like this one. This one will be omega 0. Right? It will be omega 0. This one, the real part, it will be minus eta multiplied by omega 0. Correct? So you can say that, okay, minus eta omega 0 equal -1, right? So eta will be 1 divided by omega 0. We need to find omega 0. Omega 0, it will be square root. Omega 0, it will be square root that part, which is 1. 1 minus 1 squared, it will be 1 plus that part square. So it will be 8 multiplied by, it will be minus, square root that part. So it will be 8g, correct? It will be square root of g, it's -1. The square root of g, it will be minus 8. Yeah. Yes. So we will do it step by step. So this is the underdamped solution. Okay. So this is we finished this overdamped already. So this is underdamped case. So we will find it. So the solution, g of s, it will be c of s divided by r of s equals the transfer function. We will get b1 and b2. Just remember the law, it's ax squared plus bx plus c equals 0. So x1 and 2 roots will be minus b square root plus minus square root b squared minus 4ac divided by 2a. It will be like this one. Just find coefficient of a, b, and c and solve it. So it will be this one. So it will be eta omega n plus minus g square root minus eta squared zeta squared omega n. So it will be real part, imaginary parts. So the real part will be 1, imaginary part will be square root of 8, right? The unforced component, it will include, in fact, when we use inverse Laplace transform, we will get this cosine and sine part. So from the table, it will be that part. Yes. Yeah. So both are complex conjugate, and the less eta, in fact, the less zeta here, the less damping in the step response, it can be shown that less zeta, the more dominating imaginary part over the real part of the. So anyway, we will finish here, and we will start again, continue again with the undamped system. So I don't want the videos to be too long. So thank you very much.